Welcome back to The Clean Truth by Roobi.
Glad to be here.
This is our 25th deep dive, titled Smarter Laundry Habits: How to Use Less Energy, Less Waste, and Still Get Great Results.
Yeah.
And right now, inside your home, there is a machine just consuming massive amounts of electricity.
Oh, yeah, and gallons of water, too.
Exactly. And it's probably subtly degrading your favorite clothes all because you are likely using it exactly the way you were taught to.
Right, because laundry is just one of the most resource-intensive routines happening under your roof.
It really is. It gobbles up staggering amounts of energy and detergent, often, way more than is actually necessary to clean the fabrics.
Which is why we are basing our analysis today on some highly practical guidance from the Department of Energy. They've demonstrated that simple, mechanical changes to this routine can drastically reduce your energy consumption.
Like what kind of changes?
Things like washing in cold water, committing to running full loads, using the precise amount of detergent, and optimizing the thermodynamic process of your drying habits. It lowers your environmental impact immensely.
And the crucial takeaway there is that you do not sacrifice a single bit of cleaning performance, right?
Not a single bit.
Which is the core focus today. Smarter habits naturally lead to significantly better outcomes for you personally. We're talking lower utility bills, far less wear and tear on your clothes, and heavily reduced household waste over time.
Because effective cleaning isn't about using more heat, more water, or more soap. It's about using the right amount, in the right way.
Absolutely. And that margin of precision is exactly why Roobi's laundry detergent sheets are structurally designed the way they are.
Right. By providing an exact dose in a dissolvable format, you just completely eliminate the massive plastic waste of traditional jugs.
Yeah, and you guarantee peak chemical efficiency in every single load. The product design completely mirrors the behavioral shifts we are exploring today.
It really does.
So let's break down how small changes in your laundry routine can lead to cleaner clothes, lower impact, and better results overall. Okay, let's unpack this by starting at the point of highest energy draw in the entire process.
Which a lot of people guess wrong.
Right. The biggest energy culprit inside your washing machine isn't the motor spinning the heavy, wet clothes around. It's actually the heating element.
Yes. The DOE data shows that simply switching your washer's temperature setting from hot to warm can cut a single load's energy use in half.
Wait, in half, just by going from hot to warm.
Literally in half. But the resistance to making that shift is, it's deeply ingrained in our cultural understanding of how cleaning works.
Yeah, because I know I'm guilty of treating my washing machine like a boiling cauldron. If I have heavily soiled jeans, my immediate instinct is to blast them with the highest heat possible.
You and everyone else.
I just assume thermal energy is the only mechanism capable of breaking down the dirt, is warm or cold really enough to get clothes actually clean, or are we just making a sacrifice for the environment?
What's fascinating here is that relying on thermal energy completely ignores the evolution of biochemistry. Modern cold water detergents do not rely on melting fats like the soaps from decades ago did.
So what do they rely on?
They rely on advanced enzymes. You have proteases that specifically target and cleave protein bonds in blood and sweat. You have lipases engineered to break down lipids, and amylases that dismantle complex starches.
Wow.
And these are biological catalysts explicitly designed to function optimally at standard ambient temperatures, typically between 60 and 80 degrees Fahrenheit.
So if I flood the drum with 130-degree water from my hot water heater, I am fundamentally altering the physical environment beyond those optimal parameters.
Exactly.
I'm essentially cooking the stain fighters.
You denature them. The extreme heat breaks the delicate structural bonds holding the enzyme's three-dimensional shape together, and once an enzyme loses its shape, its active site can no longer physically lock onto the stain molecules.
Oh, so you're neutralizing the detergent before the wash cycle even hits its stride.
Pretty much. Furthermore, hot water acts as a mordant for certain organic stains. It permanently sets the proteins in blood or sweat directly into the fibers of the garment.
That is wild. So by shifting to cold water, we save up to 50% of our washing energy, protect the structural integrity of the fibers from heat degradation, and actually allow the biochemistry to execute exactly what it was engineered to do.
Exactly. And the DOE pairs this temperature advice with a strict mechanical rule: manage the actual volume of water you pull from the wall. They strongly advise running full loads to maximize the efficiency of that water pull.
Right. But what if you were forced to run a small load? Like perhaps you absolutely need a specific uniform for the next morning.
Then you have to manually adjust the water level setting on the machine. Older machines and standard modern agitator models, they just don't possess the sensors required to weigh the drum's contents.
So if you place 3 garments inside and leave the dial on the default large setting,
The machine will blindly pump 40 gallons of water into the tub.
40 gallons for 3 shirts, that's absurd.
It is, which is why we are looking to dramatically reduce that water volume, especially with modern high-efficiency or HE machines.
And when we use HE machines, we fundamentally alter the physical environment inside the drum again. And that shift in physics demands a complete overhaul of the chemistry we introduce.
If we connect this to the bigger picture, the dynamic between high-efficiency machinery and detergent chemistry is entirely symbiotic.
How so?
Well, a traditional washing machine fills the entire tub, it completely submerges the clothes, and uses a central agitator pole to violently slosh them back and forth.
Right.
But an HE machine, whether it is a front loader or a newer top loader without the agitator, uses a fraction of that water. It creates a very shallow pool at the bottom of the drum and relies on gravity.
So as the drum spins, internal baffles lift the clothes out of the water, carry them to the top of the rotation, and drop them back down into the shallow pool.
Right, and that mechanical drop is the primary cleaning action. The friction of the clothes hitting the water and rubbing against each other is what forces the detergent through the fibers.
Which brings up a massive misconception that completely undermines this process. The DOE and the American Cleaning Institute are super strict about only using HE-labeled detergent. But we have been aggressively conditioned by decades of shampoo and dish soap marketing to equate suds with cleaning power.
Oh, the bubbles. People love bubbles.
We really do. We think more bubbles means more cleaning power. But here's where it gets really interesting. If an HE washing machine looks like a foam party, the machine is actually failing to clean the clothes.
Because the suds offer absolutely zero cleaning utility in a laundry environment. In an HE machine, a high volume of suds acts as a thick pneumatic shock absorber.
Wait, a shock absorber?
Yeah. When the baffles lift the clothes to the top of the drum and drop them, those clothes do not hit the water or each other with any force. They land softly on a bed of foam.
Oh, wow. So you are actively neutralizing the mechanical energy required to agitate the dirt out of the fibers.
Exactly. Not only are we buffering the mechanical friction, but we are also severely straining the machine's internal plumbing.
Because it doesn't have enough water to rinse the foam away.
Right. An HE machine uses so little water for its rinse cycle. It lacks the volume required to flush away an overabundance of thick foam. The machine's drain pump has to work significantly harder to force that aerated, viscous liquid out of the system.
Which I imagine drastically accelerates mechanical wear and tear on the pump.
Definitely. And the machine's internal sensors often detect that excessive motor strain. Recognizing that the suds haven't cleared, the computer will automatically trigger additional unprogrammed rinse cycles,
Pulling more water from the wall and keeping the motor running longer.
completely erasing the water and energy efficiency the HE machine was purchased for in the first place. And whatever residue the pump cannot clear remains coated on your garments.
Ugh. Creating a sticky microlayer that actually traps ambient dirt the next time you wear the item. That's so counterproductive.
It really is.
The margin of error is incredibly narrow, which is exactly why precise dosing matters so much. And it's exactly the variable a pre-measured product like Roobi sheets entirely eliminates.
Yeah.
You are locking the precise chemical dosage to the machine's actual water volume, stripping out the human tendency to overpour.
Which saves your clothes and the machine.
So once those clothes are efficiently washed, rinsed of all residue, and spun tightly, you are faced with the next phase of the physics equation, removing the remaining moisture without destroying the fabric.
The drying dilemma. The dryer is essentially a giant, rotating thermodynamic engine. It is a massive consumer of electricity or natural gas.
So how do we optimize it?
The DOE's guidance relies heavily on how we physically prepare the wet garments before we even introduce them to the heat. We are accustomed to sorting dry laundry by color to prevent dye transfer, right?
Right, lights and darks?
But we actually must sort wet laundry by fabric weight and density to manage evaporation rates.
I am incredibly guilty of not doing this. I'll just toss my synthetic gym shirts into the dryer alongside heavy bath towels just to save myself from running a second load. To me, a wet pile of laundry is just a wet pile of laundry.
It's a common trap. But the physical structure of those individual fabrics dictates how they hold and release moisture. A cotton bath towel is woven with thousands of tiny loops.
The terry cloth structure.
Right. That creates a massive surface area explicitly designed to utilize capillary action, drawing and holding vast amounts of water deep within the fibers.
Okay. And a synthetic shirt.
A synthetic athletic shirt is woven from extruded plastic fibers. They are completely smooth at a microscopic level, meaning the water mostly just sits on the surface.
So the synthetic shirt will release its surface water almost immediately when exposed to the hot air.
Exactly. While the towel requires sustained, intense thermal energy to evaporate the moisture trapped deep within its loops.
So when you tumble them together.
The machine's internal moisture sensor detects the wet towel brushing against the metal plates and keeps the heating element firing at full capacity. Your lightweight synthetic shirt becomes bone dry within 15 minutes.
But it remains trapped inside a 150-degree drum for another 40 minutes while the towel finishes.
Yes. You push those plastic fibers well past their glass transition temperature. This bakes the elastane, makes the fibers brittle, and causes permanent structural shrinkage. You are actively destroying your clothing just to dry a towel.
Wow. So by sorting by weight, we group fabrics with identical evaporation rates, allowing the entire load to finish simultaneously.
Precisely. And the DOE explicitly states we should be leaning heavily on the machine's internal moisture sensors to prevent that thermal damage, rather than blindly relying on the timed dry setting.
I feel like people don't really trust the sensors, though.
They should. The moisture sensor operates on a brilliant application of basic electrical engineering. There are two metal strips located inside the drum. When wet clothes brush against both strips simultaneously, the moisture completes an electrical circuit.
Oh, that's clever.
The computer monitors the electrical resistance of that circuit. As the clothes dry, they hold less water, and their electrical resistance increases. Once the resistance hits a predetermined threshold indicating the clothes are dry, the machine shuts down the heating element. It eliminates human guesswork entirely.
And that sensor data also feeds into another highly efficient setting the DOE recommends, the cool-down cycle.
Yes.
I think many people assume this cycle exists purely so you don't burn your hands when pulling the clothes out. But in reality, it is a thermodynamic efficiency hack.
It is. The dryer kills the power-hungry heating element for the final 10 minutes of the cycle, but continues to tumble the clothes.
So it uses the residual thermal mass, the heat already trapped in the drum and the clothes themselves, to finish the evaporation process. You are getting the final 10 minutes of drying energy completely for free.
Which is great, but this raises an important question regarding the environmental conditions inside that exhaust system. A dryer operating efficiently relies on unobstructed airflow, which requires strict, habitual maintenance of the machine's safety components.
The lint trap, that's the front line of maintenance right there.
The DOE mandates cleaning the lint screen after every single load.
Every single one. Because lint is highly combustible. It's essentially aerated kindling. When the screen clogs, it acts as a physical wall, restricting the hot, moist air from escaping the drum.
Right, so the machine is forced to run longer and hotter to push the air through the blockage, spiking your energy consumption.
But the secondary danger is heat accumulation, isn't it?
Yes. If the restricted airflow causes the internal temperature to spike and ignite that highly combustible lint, you have an immediate and severe household fire hazard.
Which is terrifying. And the DOE source details a highly specific, practical maintenance tip for this. They advise that periodically, you must go beyond merely wiping off the pull-out screen.
You have to get in there.
Yeah, you need to attach the long, skinny crevice nozzle to your vacuum cleaner and suck out the cavity below the screen. I actually tried this over the weekend.
And what did you find?
You pull out a densely packed, sweater-sized chunk of lint that has bypassed the screen's mesh and settled directly into the machine's internal ductwork. The volume of debris that accumulates in that cavity is shocking.
It really is. And that airflow restriction extends all the way to the exterior of your home. The DOE also mandates a thorough inspection of the dryer vent itself, the physical tube running from the back of the appliance to the outside wall.
What are they looking for?
They specifically mandate using a rigid venting material, like solid aluminum ducting.
Ah, so they explicitly warn against using those flexible accordion-style plastic vents you see stuffed behind older machines.
Strongly warn against them. The fluid dynamics of those flexible vents are terrible. The internal ridges create massive air turbulence, slowing down the exhaust velocity and providing thousands of tiny ledges for lint to catch and build up on.
Plus, the plastic is highly susceptible to physical collapse. If the dryer vibrates and pushes back against the wall, it can crush the vent, dropping the airflow to zero.
And the trapped heat and moisture create an instantaneous thermal spike, Rigid, smooth-walled aluminum venting allows for high-velocity, unobstructed airflow. It minimizes both energy waste and fire risk.
Though we also have to acknowledge the ultimate energy-saving drying protocol the DOE suggests, which requires bypassing the machine entirely.
Air drying.
Yes, air drying on a clothesline or an indoor folding rack utilizes ambient thermal energy and natural air currents. It consumes zero-grid electricity, and clothing manufacturers heavily advise it for delicate or highly elastic fabrics to permanently eliminate the risk of thermal degradation.
It remains the most reliable and non-destructive drying technology available.
But eventually, though, no matter how perfectly you optimize your loads, those physical components wear out. The sensors fail, the drum bearings give out, and the appliances must be replaced.
It's inevitable.
So, what does this all mean when you're standing in an appliance showroom looking at a sea of identical white boxes? How do you make the smartest long-term investment?
You have to look past the marketing aesthetics and focus exclusively on the verified data, specifically the Energy Star and Energy Guide certifications. The performance metrics of these certified machines compound dramatically over a 10 to 15-year lifespan.
Let's talk numbers.
Sure. Energy Star certified clothes washers operate using roughly 35% less water and 25% less energy than standard, non-certified baseline washers. Conventional Energy Star dryers use 20% less energy.
How does an Energy Star washer physically achieve a 35% reduction in water while still actually removing the dirt?
It comes down to sophisticated drum architecture and vastly improved motor torque. The internal baffles are redesigned to maximize the mechanical drop of the clothes, meaning they achieve the required friction with a much shallower pool of water.
Oh, that makes sense.
Furthermore, the direct drive motors achieve incredibly high spin speeds during the extraction phase. They subject the clothes to higher centrifugal force, physically throwing more water out of the fabric before the cycle ends.
Which means the dryer has significantly less moisture to evaporate in the next step. And speaking of the dryer, the DOE source highlights a massive technological leap that represents the future of laundry efficiency Energy Star certified heat pump dryers.
What's fascinating here is that the heat pump completely reimagines the thermodynamics of the drying process.
Right, because a traditional conventional dryer pulls ambient air from your laundry room, runs massive electrical current through a heating coil to superheat that air, passes it over your wet clothes so the heat excites the water molecules into a vapor, and then violently blows that hot, humid air out the side of your house through the vent.
It's incredibly wasteful.
You are literally paying to heat the air and then immediately discarding it.
It is an open-loop system that bleeds thermal energy. A heat pump dryer, on the other hand, operates on a highly efficient closed-loop system. It pulls the moist air out of the rotating drum and passes it over an evaporator coil filled with cold refrigerant. This drops the air temperature completely below its dew point.
So the vapor physically condenses back into liquid water right there on the coil and drains away through a simple hose.
Precisely. Once the moisture is extracted, the machine takes that newly dried, cool air and passes it over a condenser coil to reheat it. It then shoots that reheated, dry air back into the drum to absorb more moisture from the clothes.
It recycles the same air volume.
Yes, it captures the thermal energy rather than venting it outside. Because it isn't constantly heating fresh, cold, ambient air from scratch, the DOE notes that heat pump dryers save between 20% and 60% more energy than conventional models.
60% energy savings is a phenomenal long-term return on investment. And because they rely on dehumidification rather than raw, scorching heat, they operate at much lower temperatures, extending the lifespan of your fabrics.
Exactly.
Plus, because it is a closed loop, they are entirely ventless. You can install them in the middle of a hallway closet without drilling an exhaust hole through your exterior wall.
They really represent the current pinnacle of applied efficiency in household appliances. The initial purchase price is marginally higher, but the reduction in operational energy pull over a decade makes the financial math undeniable.
Absolutely. By taking just a few intentional steps, trusting modern enzymes by dropping your water temperature, perfectly aligning your low sudsing detergent dosage with your machine's water volume, like we talked about with the Roobi sheets, sorting wet garments by their physical evaporation rates, obsessively maintaining your exhaust airflow, and investing in closed-loop thermal technology, you take total control of your household footprint.
You really do.
You extend the structural life of your garment, reduce the mechanical strain on your appliances, and dramatically cut your utility bills.
It just requires a shift in intentionality. If we connect this to the bigger picture, think about how our modern obsession with more scorching hot water, overflowing scoops of chemicals, massive volumes of suds, and endless high heat drying cycles actually works in direct opposition to the biochemistry and engineering designed to help us.
It really makes you wonder.
Yeah. What other areas of our daily household routines are we actively overcomplicating and making less efficient, simply because we've been culturally conditioned to assume that brute force is the only way to solve a problem?
That is such a fascinating thought to end on. We assume maximum power and maximum inputs guarantee superior results when the physics and the chemistry prove the exact opposite is true. Thank you for joining us on this deep dive. I highly encourage you to test these mechanical shifts during your next wash cycle. Trust the science over the brute force. Your utility bill and your wardrobe will thank you. Until next time, stay curious.